EOT question number 3. Sources of error while taking measurement. Sources of error. Sources of error while taking measurement. Okay. So what are the common sources of error while taking measurement? The common sources of error, one is parallax error. Parallax error. What is the meaning of parallax error? For example, if we have a ruler and I am making the length of this marker, okay? Using this ruler, I am measuring the length of the marker. So I am starting from here, I am keeping it at a 0 and starting like this. So when I take the reading, I have to look at the reading straight. Okay, my eye level should be parallel to the reading straight. Okay, if I look at an angle like this, then the reading will be different. If I look at an angle like this, reading will be different. So I need to keep the eye level straight. Now the length of this marker is 13.4 centimeter. So I need to get the correct reading, I need to keep eye level straight to the reading. So if I keep it above like this, the reading will be different, little bit different, like 1 millimeter different. And if I look at like this at an angle, the reading will be different. This is called parallax error. Okay, so one of the source of error is parallax error. Parallax error is due to reading the instrument at an angle. Reading instrument. The parallax error is due to reading the instrument at an angle. So we should not read the instrument at an angle. So what is the correct way or correct practice of measurement? Look at the angle straight, sorry, look at the reading straight, look at the reading straight. Okay, so that is called parallax error. How to avoid this? By looking at the reading, by looking at the reading of the instrument. Okay, reading of the instrument by looking at the reading straight. Straight means parallel to the eye level. Straight means parallel to the eye level. Parallel to eye level. So this is one of the common mistake, reading the instrument at an angle. When we read the instrument at an angle, we will get an incorrect value, an incorrect measurement. So when we read the instrument, we have to read it straight. The eye level must be parallel to the reading. The next, another source of error is reaction time error. Reaction time error. The second source of error is reaction time error. So this is the first one, number one, parallax error. One more point in parallax error, if you are using digital reading, means if you are using digital instrument, there will be no parallax error. Parallax error will be associated with only the analog instrument, because in digital we are not reading, right? Means digitally the instrument is giving us the reading, but when we use the analog machine like an analog ammeter or analog voltmeter, so we have to look at the reading and decide the reading, right? So parallax error is associated with analog instrument. Analog instrument. Analog instrument. Digital instruments will not give parallax error because it will display the reading, display the correct reading digitally. So no parallax error, no parallax error while using digital instrument. So if you are using a thermometer, the analog thermometer, there is reading as in like numbers, and we need to read the mercury level like this. So that is analog instrument, so there is a chance of error, means chance of parallax error. If you are using a digital thermometer, it will correct, means it will give exact value of the temperature. So when we are using digital instrument, there is no chance of parallax error. So another is reaction time error. It happens with while using the stopwatch. Okay, so when we are using stopwatch, reaction time error is associated with measuring time using stopwatch while using stopwatch. For example, you are doing an experiment to calculate the speed of an object, speed of a toy car. So you start the toy car and it will move a distance. You will measure the distance. At the same time, when you start the toy car, you need to start the stopwatch, right? So if you are not starting the stopwatch at exact time the car starts, then you will not able to get the perfect value of the time, the accurate time. So reaction time is one of the source of error while we conduct an experiment. So when we conduct an experiment to calculate the speed of a toy car, we need to start the stopwatch when you start the car, and you need to stop the stopwatch at the same time the car stop. Then you will get the exact time, but you may not be able to start the stopwatch at the same time the car start, because there will be a reaction time. Okay, so reaction time is associated with using stopwatch for measuring time, right? For measuring. So we cannot completely avoid the reaction time, or we have to use instrument like light gauge, something like that, means automatically the switch off and switch on timer. So what can we do to means be alert? Okay, be alert while conducting the experiment and try to start the stopwatch at the same time you start the means car, if you are measuring the speed like that. Okay, so reaction time error is. Then another source of error is zero error. This is number 2, and number 3 is zero error. So what is the meaning of zero error? For example, I am measuring the length of this marker like this. So it is like a 14.3 centimeter, for example. So when I keep this, I need to keep it exactly at 0. If I am not keeping it exactly at 0, for example, if the one end of the ruler is broken here little bit, so if I am keeping like this somewhere other than 0, now I am getting 14.9. So there is a mistake in the reading, in the measurement, due to the parallax, due to what? Due to zero error. So when we start the reading, we need to keep it we need to keep it at 0, right? So that is the zero error. So in this zero error is a systematic error, means it is associated with the instrument. Okay, so this zero error is associated with instrument, associated with instrument. So this type of error that is associated with the instrument, the machine that we are using to take the measurement, is called systematic error. Systematic error. So if there is a problem with the instrument, then means if there is a zero error with the instrument, for example, we are measuring the mass of something. So I want to measure the mass of this water bottle, keeping it on the balance. So before I keep it on the balance, the reading on the balance should be 0. If there is nothing on the balance, the reading should be 0. But if it is already like a 200 gram or 100 gram reading, when there is nothing on the machine, then if I measure the mass of this water bottle by keeping it on the machine, I will get an incorrect value, because there is a 0 error. The machine was initially not at 0. Then if I repeat the measurement again, or if another student come and measure it again, we cannot get it. Means that same mistake will be there, the same error will be there. So by repeating the instrument, we cannot reduce the systematic error. We cannot reduce systematic error by repeating the measurement. To correct systematic error, we need to correct in the machine. So systematic error cannot be reduced. Systematic error cannot be reduced by repeating the measurement. By repeating the measurement, we cannot avoid systematic error, or we cannot reduce systematic error. But parallax error and reaction time error, that depend on the person doing the experiment. So the sources of error that depends on the person doing the experiment is called random error. So these two, parallax error and reaction time error, are called random error. Random error. So random error can be identified or reduced or avoided by repeating the experiment. Okay, by repeating the experiment, we can reduce random errors. We can reduce random errors. So random error depend on the person doing the experiment, and systematic error depend on the instrument that we are using to take the measurement. All summary of this: the sources of errors we have two types. What are the two types? What are the two types of sources of errors? What are the two types? Random errors. What are the two types, students? Random errors. And what is the second type? Second type is systematic error. What is the second type? Yeah, systematic error. Random error depends on what? Random error depend on person doing the experiment. Means random error depend on the person making the measurement. Okay, doing the experiment means making the measurement. Random error depend on the person making the measurement. Means when different students repeat the experiment, when different students do the experiment, the error will be different. Example for random errors. What are the examples for random errors? What are the examples, students, for random errors? Very good. Parallax error, and what is the second example? Zero error. Zero error is not correct. Parallax error and
reaction time.
very good. Parallax error and reaction time error. Parallax error and okay. Parallax error. One is example. Okay. Parallax error and reaction time error. Okay. So what is parallax error? Parallax error is, what is parallax error? It is due to, parallax error is due to taking reading at an angle. So how to reduce parallax error? By looking at straight to the reading, right? By looking at straight to the reading. The reading must be parallel to the eye level. Okay. So reaction time error also we can reduce by being alert, trying to switch on and switch off the stopwatch at perfect time. Then systematic error. What is systematic error? It is depend on what? Yeah, zero error is an example for systematic error. Okay, zero error. Zero error is example for systematic error. Systematic error associated with what? Machine or the person?
Machine.
Machine, right? Systematic error is associated with the machine or the instrument that you are using. Okay. So can we reduce systematic error by repeating the experiment?
Yes.
No. We cannot reduce, we cannot reduce systematic error. We cannot reduce systematic error by repeating the experiment. Systematic error cannot be reduced by repeating the experiment because the instrument that you are using is not correct, right? If you are using the same instrument again and again, you will be getting the same mistake. But you can reduce the reaction time error and parallax error, or you can at least identify if there is reaction time error or parallax error by repeating the experiment. Okay, by repeating the experiment. By repeating the experiment, we can reduce parallax error, means we can reduce the random errors. Okay, students, what are the examples for random errors? What are the examples for the random errors? Make it fast. Yes, parallax error and reaction time error, right? Parallax error and reaction time error. Okay, so we are continuing with EOT question number 3. Okay, EOT question number 3. So we need to discuss question number 16. Okay, yeah, read question number 16. What is question number 16? Can you read, one of you? Yes. Question number 16. A box has a length of 18.1 centimeter, right? So what is the length of the box? Length of the box is 18.1 centimeter and the width of the box is 19.2 centimeter. Width equal to 19.2 centimeter. And what is the height of the box? Means how tall? 20.3 centimeter, right? So height of the box is 20.3 centimeter. The part A of the question, what is its volume? What is the volume of the box? How to calculate volume? If it is a box, volume of the box is length multiplied width multiplied height, right? Volume of box equal to length multiplied width multiplied height. So this is how we calculate the volume. By multiplying all the three sides we can get volume. So length is how much? Length is 18.1 centimeter. So 18.1 multiplied. Width is 19.2 centimeter. So 19.2 times height is 20.3. We will use the calculator. So when I use the calculator, what is the value I am getting? How much?
7,054.646.
How much? 8.
7,054.
Okay, let me check. 18.1 times 19.2 times 20.3 equal, yes, 7054.656, right? 7054.656. Okay, so length is in centimeter, right? This is in centimeter, this also in centimeter, this also in centimeter. So there are centimeter times centimeter times centimeter, right? There are 3 centimeters. So volume will be in centimeter cube. Okay, the unit of volume here is centimeter cube. Okay, then is our answer correct? Actually this answer is not correct in significant figures. Okay, this answer is not correct if you are writing the answer in, if you need to write the answer in correct number of significant digits. For example, here how many significant figure? In 18.1, how many significant figure? Very good, 3 significant figures. In 19.2, how many significant figures? Also 3. In 20.3, significant figure is 3. So we need to write the answer in 3 significant figures. We need to round the answer to 3 significant figures. Here in our answer, how many significant figures? There are 7 significant figures. That is not correct, because in the given values there are only 3 significant figures. So when we write the answer after the calculation, we need to write the answer also in 3 significant figures. So we have to round the answer to 3 significant figures. How to round this to 3 significant figure?
Can't be 7,000.
Yes, we can write like this: 7050 centimeter cube. So if you write 7050, this is a whole number and the last zeros are not counted as significant figure in a whole number. That we will discuss, okay, in the next question, how to count the significant figures in a given number. Okay, so this is the answer. Then part B of the question. What is part B? Read part B. Part B of the question is, how precise is the measurement of length of volume? What is the precision of measurement of length? Precision of measurement of length 18.1. So 18 means a measurement is given. If the measurement is given, how to know the precision? Do like this. This is our measurement is what? 18.1 centimeter. So what is the precision? Precision is 0.1. Okay, precision is 0.1 centimeter. Okay, for example, here in width 19.2 centimeter. What is the precision in 19.2? Make means the first digit we will make 0, second digit also 0, the last digit we will make 1. What is the last digit here? The last digit is 0.2, so we will write 0.1 centimeter is the precision. 0.1 centimeter is the precision. Then what is the precision in volume? What is the precision in volume? Precision in volume is, this is the value of the volume, right? 7050 centimeter cube. There is no decimal in volume. So precision of volume is 1 centimeter cube. Okay, precision of the volume is 1 centimeter cube, because there is no decimal, right, in this. Okay, then how tall is a stack of 12 of these boxes? The height of the box is 20.3, right? The height of this box. So you are measuring the volume of the box, right? Like this box. So its height is, the height of the box is how much? Height of the box is 20.3, right? 20.3 centimeter. Then if you keep 12 boxes like this, okay, so what will be the length, means height of the 12 boxes, height of the stack of 12 boxes? So that we can add this 20.3, we can add 12 times, correct? Add 20.3 12 times, like 20.3 plus 20.3 plus 20.3 plus 20.3 plus, like that. So if I add like that, 20.3 plus 20.3 plus 12 times, I need to write this, right? 20.3, that is actually equal to 12 times 20.3, right? 12 times 20.3. So 12 times 20.3, what is 12 times 20.3?
43.6.
Very good. 12 times 20.3, 243.600, right?
Yes.
243.6 243.600 centimeter, right? The answer will be in centimeter. Okay, so here what we are doing, here we are adding, right? Here we are adding, right? Adding. While calculating the height of the stack of the boxes, we are adding. Here what did we do? Here we multiplied, right? Here we multiplied. So while multiplying or dividing, when we are multiplying or dividing, we will write the answer in correct number of significant figures. While multiplying and dividing, we need to write the answer in correct number of significant figures. Okay, but when we are adding or subtracting, we need to write the answer in correct number of decimal places. While adding and subtracting, need to write the answer in correct number of decimal place. Okay, so here in this one, in 20.3, we are adding 20.3, 20.3, 20.3, like that. How many decimal place is here? Decimal place means number of digit after the decimal. How many digits are there after the decimal? Only one digit. There is only one digit after the decimal. So in our answer also, there should be only one digit after the decimal. How many digits are here in this answer after the decimal? 3 digits. So we should not write like that. We need to write in correct number of decimal places when you are adding or subtracting. So here we are adding, so we need to write like this, 243.6 centimeter. Then our measurement and our calculation or our reading is correct, because the numbers we are adding, the smallest number of decimal place is 1. So our answer should also have one decimal place only. There should not be more than one decimal place, because in the numbers we are adding, there is only one decimal place. And here also, but in multiplication or division, we do not count the decimal place. Okay, we need to count the number of significant digits. So here 3 significant digit, 3 significant digit, 3 significant digit. So we will write the answer in 3 significant digit. Okay, we need to round the answer to 3 significant digit. Okay, the next part D of the question. How precise is the measurement of the height of one box of 12 boxes? So precision of the height of one box 20.3, right? So one box is height is 20.3 centimeter. So what is the precision? If this is the reading, how to write the precision? Make the all the digit 0 and only the last digit 1. All the digit 0. Okay, 20 means 2, 0. This we will make 0. Last digit we will make 1. So this is the precision. Okay, precision is 0.1 centimeter. So in volume, sorry, in the height of the stack, height of the stack is 243.6. What is the precision? How to write the precision? Make all the digit 0 and the last digit 1. So 243 all will become 0. Point last digit 1. 0.1 centimeter is the precision in that reading also.